Okay, looks like we can start. Welcome back, everyone. So we're just about ready to finish off week 6, and not too many really big announcements so far. We have our quiz that's due today, quiz 4, and the brand new quiz 5 posted as well. Quiz number 5 is going to be mainly topics from section 6.1, it turns out. And once we get through 6.1, we'll start factoring in earnest, starting in section 6.2. 6.3 is going to be more factoring topics, really just here in case we have time to get into those notes, but mostly we'll be looking into that next week. Section 6.4 is just going to be a review of factoring techniques. So that'd be kind of nice to review all of this at once in one section. And then the next section we'll be looking into solving equations and doing applications with factoring. As far as the other announcements go, it's kind of dry, except we do have a second exam that's coming up on this week here. So it'll be Tuesday, October 21st. It is a ways away. So once we get to about Friday of this week right here, I'll have a good idea of what's going to make it for the content exam 2 and start including that information. But at the moment, as long as you're keeping caught up on your quizzes, your exams, you pretty much are studying for the exam 2 content. And I think that's pretty much all I have for the announcements at the moment. Any questions or comments so far? Or any questions to start us out? Okay, well, I believe we got to like the first parts of the first example here. So let's review what we were doing there. We're looking into finding the so-called greatest common factor, or GCF for short, is the big acronym that just about every math book uses. They could occasionally say greatest common divisor because, well, that's what it does. It's the largest thing that divides all the expressions in your list. So when we looked for the greatest common factor of 45 and 120, we found it was 15 because no number higher than that would divide both of the numbers simultaneously. Now, only thing new in part B is there's variable expressions there. The numbers are a little bit more tame, so easier to work with. And some people are pretty good at just eyeballing these and telling what the greatest common factor would be just by visual inspection. But for the sake when the numbers are a little bit larger, like on part A, let's redo the factor tree approach. 28 itself can factor by first dividing it by 2, giving us 14. Divide that by 2 and we get a 7. And then the factor tree terminates since 7 is prime. Then rinse and repeat for 42. We can divide that by 2 to get a 21. Next divisor is 3, goes in 7 times. And we see a greatest common factor between them. It looks like it's going to be 14. The factors that are in common are the 2's and the 7. It's not the full story because we also have to deal with the variable parts, x squared y power 4 and x power 4 y power 4, but this gets us started. So if you like this kind of technique, we could redo it again for visualizing greatest common factor. I'll rewrite out this term right here, 28x squared y power 4 could be rewritten as, it's really just a 2 times 2, or 2 squared, times, I'll leave a little bit of a space because there's also a factor of 3, and put times 7. Then there's x squared, y power 4. Likewise for the second term, 42x power 4, y power 4, we can rewrite this as, seeing the chart here of prime factors, this one's 2 times 3 times 7, then the variable part, x power 4, y power 4. From there, we can get the greatest common factor in just one quick glance at what the table's telling us. The idea here in orange, we just use again, the largest thing that's going to divide both this term and this term is going to be going across every one of these columns, the 2 column, the 3 column, 7 column, x and y column, and take the minimum power we see. So in this column, we have to take 2. We can't take 2 squared, that'd be 4, and that's just because, well, 4 didn't divide 42. There's no 4 when we look into the factors here. So we just take the 2, the minimum power. Here there's no 3 whatsoever, so we can't take 3 at all. We just skip down to 7. We need the common factor, so this is going to be times 7 from that column. Here we take the minimum power, so x squared. This one's a tie, so we just take y power 4. And 2 times x7, y power 4, or rather, if we simplify it, 14x squared, y power 4, is the greatest common factor. It's the largest expression in terms of, that's the biggest number, 14, that divides both 28 and 42. And these are the highest powers on x and on y that would do the same, dividing into this one and into this one. So what we really want to do is factor out to the greatest common factor, but this gets us started, just knowing what the greatest common factor is in the first place. Well, any questions, folks, on getting through part B? Okay, well, chapter 6 is all about factoring, and the greatest common factor is, in a real sense, the most important topic in the sense that there's going to be other factoring techniques. If you notice there's a greatest common factor, and your number one step is you factor that out, you make a lot of problems, which could have been difficult, really hard to start, much, much easier to approach. So here's what factoring out the greatest common factor would look like. First, for just kind of a review type of a problem, let's discuss the distributive law. The distributive law we've already used quite a few times already in this course, but it's a good idea to just write it in right here because this is what factoring out the greatest common factor is all about. The distributive law says if we take A times B plus C, we get AB plus AC. In other words, if you like arrows, A can multiply the B and it can multiply the C. It says you don't necessarily have to follow order of operations, which would have said add first. You can distribute, multiply these things, and then add. So you get options through the distributive law. So this is what the distributive law would look like. But if we're doing the other technique of factoring out the greatest common factor, it looks like this instead. We start off by taking AB plus AC. Curiously, the same exact thing on the left side here. It has a common factor. A is right here. Factor just means it's multiplying that term. The factor A is here as well. And if there's a factor in common, factoring out looks like this. We pull A out and we leave behind B plus C. Essentially, all we've done is we've divided A out of this term, leaving a B. We've divided A out of this term, leaving a C. But the keen-eyed would observe, that's just the distributive law in reverse. That's literally all it is. So that's what we're going to do in these problems. Really, the rest of this notes, we'll be using the distributive law in this format, going from the left to the right. And that's what we mean by factoring. What any questions with the distributive law and reversing it? Okay, so factoring out the greatest common factor first means you have to spot the greatest common factor. The way this would go is we observe just for the numerical part with 5 and 25, 5 divides both. It's the largest number that would do so. So we would begin by putting down a 5. Then between x squared and x, the largest power of x that divides both of these at once is not x squared. It divides here evenly, but not over here. The highest power of x that divides both is just x itself. In other words, we're doing the same idea here, where we're taking the minimum power. Once we have that 5x there, the process looks just pretty much exactly what we did over here. Whatever the greatest common factor is, it's dividing each one of these terms. And we don't always write this step, but we might as well do it this time just for the emphasis on that technique. If we divide 5x squared by 5x, then the 5's would cancel. X goes into x squared, x many times. And that's our last section, 5.2 exponent laws working for us from last class. So that means factoring out 5x here just leaves behind x. We copy the sign in the middle, minus. Then we do the same thing, 25x, divide by our greatest common factor of 5x. This time it's the x's that cancel. 5 goes into 25 5 times. And so we just copy in x minus 5. So that goes here, this goes there. Just the result of dividing out the greatest common factor. Let's highlight that just for emphasis. And this is what we get. We did it, folks. That's our very first bona fide factoring problem of the entire semester. We'll do quite a lot more, but this gets us started. Next thing you can think about with this after we get through it is there's always a check when you factor. The check is literally the distributive law. So if we rewrite this as 5x, x minus 5, and do the check, we would take 5x times x. That would be 5x squared. Then it will be 5x times the negative 5. That would be negative 25x. That's indeed what we started with right over here, 5x squared minus 25x. So the check is complete, and this is the answer right here. Just because there's a lot of details here, I want to put that in a box just to emphasize when it says factor out the greatest common factor, this is what your answer would look like. It has to include the greatest common factor, and then the thing it's multiplying in parentheses. Well, that's our first one down. Any questions at all getting through that one? Okay, so that was kind of a nice one to get started. Some of them look kind of involved like this one. There's 3 terms this time. Well, the distributive law could have been written with 3 terms in the middle. We just started off with 2. So it doesn't matter how many terms we have. We can always factor in this way. Let's go in order of how you probably want to attack this. Instead of looking at it as a whole, just focus on the parts. The coefficients are 3, 15, and 9. The largest thing that divides all of them would just be 3 itself. It goes in here once, here negative 5 times, here positive 3 times. So the first part of our greatest common factor involves a 3. Then the next thing we look into is the variable involving base x itself. There's a power 5, a power 4, a power 2. But remember the comment from before, we always take the minimum power. So for x, we would be taking x squared. Then we run through it all over again. Look at the the factors involving y. There's a y power 4, y power 5, y power 7. We take the minimum power, y power 4 will do the job. So the greatest common factor is 3x squared, y power 4. We've opened a parenthesis, and now we're going to just put in the result of dividing all 3 of those terms, here, here, and here, by this greatest common factor. So there's a couple ways to do this. We don't always write down this division in this way. Sometimes we just look into this right here as a divisor and see what would cancel. The 3 would divide off immediately when the 3 divides here. X power 2 going into x power 5 would leave us x cubed. Then finally, y power 4, when it divides into this y power 4, is a clean cancellation. And so this would be our entire first term. We also want to imagine, what does the check look like each time we build a term? If we did the check, we would distribute this way. When we multiply that, it would be a 3, x squared times x cubed. That's our exponent laws. That would be x power 5. Doesn't hurt to write that down over here. That gives us back to the x power 5. The y power 4 doesn't increase in size, so we would just get back the y power 4. So if we use the distributive law, we'd get the 3 in front, the power here goes up to 5, and the first term comes right back. Then it's rinse and repeat. We do it again for the middle term now. The positive 3 divides the negative 15, leaving a minus 5. X squared in blue would divide into x power 4, but that just leaves an x squared. Y power 4 would divide into y power 5, but that just leaves y to power 1, so y alone. Then one more time, 3 goes into positive 9, positive 3 times. This time, this x squared divides into this x squared, and it's just a clean cancellation. X squared's gone. Y power 4 divides into y power 7, but that would just leave behind y cubed. Then that would be our whole answer on that one. If we use the distributive law, we would just distribute this thing in blue, the greatest common factor, into all 3 terms, multiply, combine like bases using exponent laws, and we would get this original thing right back. So definitely kind of more involved, but just go step by step, term by term by term, and it's not too different than what we did in part A. Well, that's 2 down so far. Any questions at the moment getting through either one of these? Okay, the next one's a little bit weird. But if you think in terms of what's common as a factor, the same idea applies. There's a 3x plus 4, but it's in parentheses. That makes it a bona fide factor in its own right. Between 5 and 2, the greatest common factor is 1. So factoring it out, that's just dividing by 1, and it causes no difference. So we ignore the 1. There's an x alone and no x here, so x isn't involved as a factor as well in the greatest common factor. This time, the greatest common factor is 3x plus 4 itself, that entire group. And notice that if we did distribute 5x into this group, distribute 2 in this group, that would actually be going backwards. It would make the problem harder. It was actually helpful to have that 3x plus 4 in parentheses, because now when we go to factor it out, here's what the visual looks like. Factoring out, say, like the 5x up here, literally meant we are dividing that greatest common factor of 5x into the first term and just writing what's left over. It works for even this stuff. If it comes in as an entire group, if we factor it out into the left, like we did on all the other problems, it would mean this is just divided out. It cancels, and it leaves behind 5x. Then plus, because the middle term is positive, the 3x plus 4 as the greatest common factor also cancels this entire term, leaving behind 2. And at this stage, the whole problem is done. It was like it was just set up to go really nice and smoothly. Any questions on getting through that one? I think it's definitely kind of hard to visualize. Okay, part D, that's weird. It's called part D. I think I forgot the alphabet. That should have been at part C, rather. Part C's really major purpose is to help us see how it works when we do the factoring by grouping technique. Let's move this up a little bit just so we can see the last problem right here in view of this one we're about to do. So factoring by grouping, whenever you see this come up in this course, it's exclusively going to mean we're dealing with 4 different terms. Essentially what we have is not a greatest common factor for everything, but in groups we can find individual greatest common factors. So notice that the first 2 terms here, 2t minus 8, if we consider that to be an entire group, that alone has a greatest common factor of 2. 2 divides the 2 and then minus 8, so that would be a greatest common factor. Likewise here, the variables are kind of strange, s and t, but notice s appears in both terms, the first term and the second term. That means it has a greatest common factor equals to S. And that looks like the number 5. That's one of the reasons I don't like the variable S. It's easy to get mixed up between the number 5 and the letter S. So if we can find groups where there are greatest common factors, sometimes it's beneficial to just actually factor them out. Here is what this would look like if we did just that. Starting in the first group, we're factoring out a 2. That means right here, we divide by 2. That just leaves a t. Minus, divide by 2 here, and we get a 4. We do it all over again. We have a plus here, and we're factoring out a positive s. When we factor out s from these terms, s cancels here by the red dot, leaving t. S cancels here on the negative 4s, and it just leaves a minus 4. But notice t minus 4 shows up on both terms. It's just the same as this last problem where 3x plus 4 showed up twice. We can just factor that out. It would look like this. Take t minus 4 because it's common to both. It factors out here. And then it leaves behind, well, it's essentially canceling when we factor. It cancels on these two terms, leaving behind 2 plus s. So that would be the entire result on the factoring by grouping technique. It means in this course, you'll have 4 different terms. You're looking for 2 greatest common factors, and they're probably going to be different, almost guaranteed. But just factor them out, and you do a problem that's essentially a do-over of the part C that's right above. Factor out the 2 groups, t minus 4 from this factor and this factor, and our work is done right at that step. Well, any questions with that one, folks, getting through it? Okay, let's do a quick check on this one. If we were to multiply this out, we're supposed to get all of this right here. The check is easier on something like this one because sure, the second factor, I'm getting this backwards today, factor is the thing that you're multiplying. The second factor has 2 terms, and the first factor is just a 1 term, 5x. So this was an easier check to get through. This is 2 factors here, both with 2 different terms. The terms are being separated by pluses or minuses. So the check is a little bit different, but you know what? There's a great acronym for this. It'll be the FOIL method. So if we want to check this out, we'll take t minus 4 multiplied by 2 plus s. We need to get back this original thing right up here. So let's get started. FOIL method means you would first multiply here. That's the F in the FOIL method because it's the first terms that appears in both groups. This is t times 2, or you could write it as 2 times t in this way. Then multiply here to here. That's the O in the outer because this is the far left. That's the far right. So O for outer. It's following the arrow, t times s. So we'll go plus ts, or st if you prefer. Then multiply here to here. This is the I part of the FOIL method. I standing for the inner. That's the 2 inner values here to here. 4 by negative 2 just gives us a minus 8 pretty quickly. And then multiplying here to here, that's L for last, and that makes out the acronym, the FOIL method. That'd be negative 4 times s, so minus 4s. Essentially, all we do in the FOIL method is we take t, we distribute it into this group, then we just move over to the next term, take negative 4, distribute it into this group. Even if there was 3 terms here, we would just follow that same exact pattern. And this definitely looks odd. It wasn't written that way, but when it comes to these additions and subtractions, we can rearrange the order. This is just the same as 2t. Let's bring in that first, minus 8 plus st minus 4s. So the check is complete here, but this is just to make it easier on our eyes. It's now in the same exact order as how the problem came. So factoring by grouping, really it's just a way to undo the FOIL method. That's kind of cool in a way, and we'll take advantage of this in the next section with something called the so-called AC method for factoring. But the answer was right here. Once we got to this stage, our work was done. Any questions with getting to that spot or with the check itself? Okay, let's try out the last example in the notes. Oh, and I should have mentioned, I forgot to say so. I noticed a typo when I was looking into these notes just earlier today. That value right there should have a power 3. So sorry if you printed this out already with a typo or downloaded it. Correct that to a power 3, and that's the problem that would actually work out. It's not a factoring by grouping problem at all if that was an x squared like it was originally. So here's the method once again in factoring by grouping. In the first two terms, find the greatest common factor. The biggest thing that divides both of these, it can't be x because it doesn't appear in this term. It can't be y because y does not appear in this term. Looks like it's just going to be a 2 again on this one. Then do it again for the last two terms. There is something new on this one. It's separated by a negative sign, and that's actually kind of important to watch out for. Whenever there's a negative sign, we have to be careful of what we actually factor. And you know, when we call this the greatest common factor, it's a little bit of a lie. When we say the, we're acting like there's a unique answer. The is the definite article, meaning only one greatest common factor, but you actually have choices. You could divide out by -2 as well. It would just have been an odd choice on this problem. Dividing by -2 here would have gotten you -3x, +2y. But usually we would have factored just by about the +2. However, in factoring by grouping, when a negative sign shows up right there, you want to take the negative greatest common factor. So let's make a big deal out of that right here. Strongly indicates we should factor out a negative as well. This will come up in a few spots in the homework as well, so watch out for that negative in the middle. If we don't factor out a negative, we actually don't have the repeat of two terms that we saw here and here. They're going to be off by a sign, and it feels like we're just stuck. But factoring out that negative is what fixes the whole operation. So what we'll factor out on this one is a greatest common factor of negative. So now we made sure we're taking out the negative sign. And what else? Well, there's an x cubed and an x squared. So we can factor out to the minimum power, x squared itself. Y doesn't appear on this term, so we can't factor out y. And the coefficient here is 1, so we can't factor out -3 either. Looks like that's the best we can do, a -x squared. Let me use the arrow method. So once we get there, we start to do the actual factoring. First, on these two terms by the red dot, factor out a 2. 2 will divide here, leaving a 3x. It divides here, leaving a -y. Now next we're factoring out the -x squared, so we write that in immediately. You'll notice whenever we factored out a greatest common factor in these notes, we always factor it out to the left. That was just to make the pattern easy to see what's going on visually, but also means the negative side moves to the left as well. So back over here, when we factor out x squared, we're also dividing x squared from this term by the red dot. We divide out the negative as well, so this is just going to be a +3x. Factoring out a -x squared here is going to flip the sign on us. And it better, right? Because we're expecting a negative. If we put jump down to plus y, we're stuck right at this step. These terms have to be identical to proceed to the very next line. But we're factoring out negative x squared, so this was positive becomes negative y after we divide the x squares and divide by -1. So now at this stage, we're in business. We have 3x minus y identical to 3x minus y. We can factor that out in the next step. I like to connect these with equalities, so let me force in that equality there. And here's the next equality. Once you get to this spot, the main difficulty in the problem is over. We just write in 3x minus y. Observe, that means we are literally canceling these out through division and just writing down the survivors. It's just 2 minus x squared. Then that does it for the problem. The answer would be 3x minus y times 2 minus x squared. And you can give these in either order. If you factored this to the right, you might have put it in the answer, parenthesis, 2 minus x squared, times over here, parentheses, 3x minus y. That would be a completely acceptable answer as well. Both these are the main things we have to be ready for when we're going into the next sections, sections 2, 3, 6.2, 6.3, 6.4. Sorry, we're not in chapter 2. Any questions at all before we close out the notes and take a look into 6.2? Okay, really pretty short section, 6.1. These are kind of unbalanced because the next sections, 6.2, 6.3, are a little bit longer. And here's how the next one goes. The title is Factor Trinomials. Again, this book is weird. The title is a command of some kind, but we'll just go with that. That is what we're going to do. We're going to factor trinomials. The first thing that's kind of mysterious about this is, what is a trinomial? A trinomial is a kind of polynomial, and then that just begets another question. What's a polynomial? So before we start factoring trinomials, let's do the important work of just saying what they are. In fact, there's kind of layers to this definition. A monomial could be something like this. These are all just random examples just to illustrate what a trinomials will look like when we get to that level. A monomial could be something along these lines, maybe a -10 x squared y cubed. It'd be just a random algebraic expression. It's a monomial because it has one term. There's no other +5. There's not minus x squared y. So if there's just one thing here, multiplications throughout, this would be one term. And that's where the mono part comes from. We're saying an algebraic expression where the variables are raised to integer powers like these, but just one term. Next are the binomials. So we have binomials. That could be something like this. You know, this was a monomial just as it stands, but you make one small change, go -10x squared plus y cubed. Now it's a binomial. What made it a binomial is we're separated out the factors that were all here with either an addition sign, like was in this example, or a subtraction sign. Now there are two terms. The first term is -10x squared. Second term is y cubed. And that's what the bi is just referring to. We have a polynomial expression, but now two terms altogether. Finally, that takes us to the trinomials. Trinomials, well, we're looking down at them down below. Just another random trinomial could be something like z cubed plus 43c squared minus 8z. Kind of a complicated one, variable z, just because it can be any variable we choose. What makes it a trinomial is the fact that it has three terms. And every one of these expressions we could call just overall polynomials. Well, hang on, let's call just the first two polynomials. Poly just meaning plural, more than one or many. So these would be what we mean by polynomials. This would be a monomial. The thing we're going to factor is the trinomials. So we're going for these kinds of things, trinomial expressions. Factoring them means we want to break them up into something times something, separated with by parentheses and such. And really, that's exactly what we were doing in the last sections. Those last problems were factoring into two binomials multiplying each other. But all these don't have four terms, so it's a little bit different to start this out. Just for another warm-up before we launch into the examples, let's FOIL one more thing. Let's FOIL something along the lines of, let's make it be 3x plus 7 times x minus 3. And I guess this needs instructions. Let's say multiply. Let me put this a little bit lower. So if we see something like this and the instructions tell us to multiply it out, all we're doing is the FOIL method. We take this 3x here, multiply it by x, so it's 3x squared. Multiply it against -3, so it's a -9x. Then we move over to the 7 and distribute it into the group. That'll be plus 7x. Here to here will be minus 21. Next concept is like terms. We have like terms, the -9x and the 7x. So 3x plus 7 times x minus 3 is also equal to 3x squared minus 2x minus 21. So if we go from left to right, we're multiplying. So this is the multiply by the FOIL method direction. But that's not actually what we want to do in this section. It turns out that this result, even though it kind of looks nice in some ways, it's more complicated than we need it to be. When we go to solve equations, that's not going to be helpful to us. Solving equations is easier done if it's factored like this, and we'll see all the reasons why later on in this chapter. So when it says to factor the trinomial, it means we're going in the opposite direction. Much like in section 6.1, factoring out the greatest common factor, well, that's just the reversal of the distributive law. So going this way, that's what we want to do. This is factoring. Our goal. So we want to reverse the process that expanded all of this out and get to this. That's going to be our answer. A binomial times another binomial. So here's how it's going to all start out. Any questions first with any of the warm-up topics? Okay. For some people, you might be pretty well refreshed on doing these factoring techniques. Some people might be a little bit more rusty. Again, a lot of people come to this class with pretty different backgrounds. So we're going to attack this as if you've never seen it before. It might be a pretty good refresher. Let me not show two problems at once, though. That's kind of overwhelming. So in the view of this arrow, the direction we actually want to go, we have an expectation of what our answer should even look like. It should look something like this. We just set up two sets of parentheses in that way. There's going to be binomial expressions here and here. And in a literal sense, we're just reversing the FOIL method that got us to this if we multiplied in this direction. So when we FOIL things out, recall the first thing we did was we multiplied here to here and got 3x squared. That was our number one step. Now that we're going backwards, we wonder, what can we put here? And what can we put here that would result in an x squared if we multiplied it out. Well, one thought is x times x is x squared. Again, that's our section 5.2 exponent laws working hard for us. We know x is power 1, x is power 1 here. So x times x is x squared. So in a certain sense, we're 33% done. We already know we're going to get x squared if we FOIL out this answer. So that's awesome. Now, next thing that could happen that's going to help us out is we're eventually going to multiply these terms. When we multiplied here to here, we got the negative 21 that you see right there circled. It implied something about the signs, though. To get that negative 21, you had to have a negative sign and a positive sign. That's the only way you're ever going to get that negative 21 when you FOIL out this answer. So this one's different. The 30 there is positive this time. If you get a positive here and a positive here, it implies immediately that the signs in the middle are both positive. So plus and plus. That's an important enough concept to make a big deal out of it. So let's put down something on the notes. Positive here. Let's say it this way, positive in these places gives two positive signs. By the two positive signs, we're referring to this one and this one. That's really important to kind of think in those terms because the method we're using is so-called the trial and error method, which is kind of an uncomfortable thing to think about in mathematics. You usually think of a definite answer, a definite process, but we're guessing on how to factor this. So we want to make as an intelligent guess as possible by taking out as much trial and error as possible. And already know that the signs are positive and positive means we don't have to try out things that are just guaranteed to not even work. So still, we need to get that 30, much like we have that negative 21 there. So we need two things to multiply that's going to give us 30. And then when we FOIL out the rest of the problem, we need to get 13. Anyone happen to know two good numbers that could do it? If you're not sure, one thing to try is just look at the different ways you can multiply two numbers to get 30. For example, 30 could be rewritten as, usually it would start low, something like the lowest divisor would be a 3. 3 times 10 could do the job. So if we try out, say, a 3 here and a 10 here, well, we know for sure that when we go to FOIL out, much like what we see up here, the 3 times the 10, yeah, it's going to give us a positive 30. So the 30 term is decided as well. If we get the 13x, our work is completely done. So oftentimes that's the hardest term to nail down when you're reversing this and trying to factor. But the way you get the middle term is you would multiply here to here. That'd be 10x. You multiply here to here, that'd be 3x. That's much like when we multiplied here to here, that was the negative 9x. Here to here, that was the 7x. And the negative 9x, the 7x, well, they became the negative 2x altogether. So if we add up the 3x and the 10x, we do get the 13x. And it tells us our work is totally complete on this point. The answer is x plus 3 times x minus 10. And there's really no further checking we would have to do at this spot. Because there's lots of notes here, I just want to convey that's the answer right at that step. What any questions, folks, on getting through that one? Okay, well, this is pretty much how it goes in this section as far as the trial and error method goes. So if we were to try out another one just like it, here's how this one would start out. Y squared plus 10y minus 24. Well, first, if that's a trinomial, we're expecting two binomials to multiply. Y squared could factor as a y times a y, so that's a good start. And now we analyze the signs. Well, the important thing is really this sign here. The negative 24 tells us signs must be opposites. In other words, we need a positive sign and a negative sign. That's the only way we multiply here to here and get a negative number by the law of signs. So let's just go positive and minus. Last thing we need to do is figure out a way to work with a 24. So sometimes there's a good amount of scratch work on this. 24 we could write as 2 times 12. And you know what? That looks about right. We put a 12 here and a 2 here. Let's check out how this might check. The major part of the check is taking this times this. That's the 12y. Then take the outer product. That's negative 2y. When we add positive 12y minus 2y, we get the middle term positive 10y. It tells us that was a success. The work is done right at that step. Our problem factors is y plus 12, y minus 2. And we didn't even check out y squared, but we didn't have to because we already knew if we FOIL this out, y times y gave us the y squared. And because we were working with factors of 24, we already knew this times this is the negative 24. We arranged the signs just right as well. So you're going to notice a pattern in these checks. It's always the inner product and the outer product to try to nail down the middle term. That's the most important thing. Well, let's try it out again in part C to see just how wild this can get. Any questions at that so far? Okay. So for part C, we have something that's positive and something that's negative. It's a whole new situation as well. But you know, the thing about positives are a negative times a negative does give a positive. So looking at these three different examples, this is another thing that gives you definite information. A negative here and a positive here, this implies both signs negative. And these are the three different things that can happen. Either your signs are the same, both positive, either your signs are opposite, a positive and a negative, or your signs are the same again, both negative. These are the only three things that can happen for the signs. It's kind of comforting in a way because that, again, narrows down all of the trial and error in this problem. Thinking of this in terms of the signs, we can just drop down two negative signs just like that, and we are guaranteed to be on the right track. Next, we factor b squared. It's b and b that does the job. And finally, we're looking into factors of 32. Well, we want our factors to add up to negative 12. So whatever we put here, where the red dot is, has to multiply b. And whatever we put here has to multiply b as well. Those things have to add up to negative 12. So let's take a look at our options here. Well, 32, we could first factor as 2 times 16. But if we subtracted these two, negative 2 minus 16, that's a negative 18. Not quite where we want to go. So let's look into another possibility. Let's see, 32 could also be, how about 8 and a 4? If we put in a minus 4 and a minus 8, that looks like it should do the job for us. Go minus 4 minus 8. Let's complete the check. The inner product is negative 4b. The outer product going here to here is negative 8b. Negative 4b minus 8b is indeed negative 12b. So at that very moment, the work is done. This is the factorization. And that's one thing that's kind of cool about these factorizations in algebra is they are unique. There is exactly one and only one way to do this. So it's like trying to crack a combination, numbers that multiply in a certain way and add up in a certain way. And there's only one way to make this work. So that's factoring so far. The leading coefficients to all of these polynomials have so far been a 1. And that's helped us out because that's eliminated a lot of trial and error. But it doesn't have to be a 1. There could be some other number in front of those. And that's what's going on with this one right here. Leading coefficient of 7 changes up things a little bit. The way we analyze the signs is still the same, so that's going to help us out. And the fundamental process of trial and error still doesn't change. We want to put something here, so that when we go to multiply it out, we get 7x squared. It's actually really helpful that that number is a prime 7, because if we go 7x and x, that's the most sensible way to factor 7. It's just 1 and 7 that divides it. 7x times x does give us the 7x squared. So it tells us we're on the right track with that. Next, positive here tells us both signs are positive on the middle. So go plus and plus. And here's where the actual trial and error would be in this problem, dealing with factors of 12. Well, let's see, what can we do with 12? 12 could be something like 12 times 1 if we needed it. 12 could be equal to, say, 2 times 6, maybe 3 times 4, and that's about the only options I have if I'm just using integers. If we thought of, say, like a 3 and a 4, we'll check our answer and get here to here 3x, here to here 28x. This would add up to 31x, but that's not going to work out. We're shooting for 85x. So it is trial and error. Sometimes we just don't hit it right away. It means probably pen is not a great use for tool for this kind of problem. We'll go off to the next one. But you might look before you leap. 85 is really, really big. How are we going to get to a big number like 85? What if we put a 12 here? 12 is a good thought because 7 is going to multiply that 12. And 7 times 12 is 84. That would be 84x. We're just one off. We need to get up to 85. We have to use factors that will multiply out to 12, so we're forced to putting in this one right here. But 1 times x is just x, and now we have x plus 84x's. That nails the 85x. And so, with that middle term solidified, this would be the answer. 7x plus 1 times x plus 12. So even though the method is trial and error, sometimes if you just look at the size of the numbers you're trying to get to, we would have never tried out these numbers. We would have noticed we need to put a lot of leverage with the biggest number possible right there to even have a chance to get anywhere near 85. Well, that's factoring trinomials so far. Any questions with these at the moment? Okay. If you're thinking in terms of greatest common factor as you are looking at these problems, then good on you. That's always the right thought to have. This one didn't have a greatest common factor because the prime 7 doesn't divide 12, doesn't divide 85 either. This one didn't have any good greatest common factor because the coefficient was 1, so I can't do anything with the 12 and the 32. But look what's going on with this one. 6, 10, and 4. You can divide 2 into all 3 of those. And there's more. It goes x cubed, x squared, and x. If the variable x appears in all 3, that's a greatest common factor as well. So this is one of those problems that would actually be really hard to figure out how to break down like this. But if you use the greatest common factor as a tool, it's much simpler. We'll start off by doing this. 2 divides all of the terms, and so does x. So here, first, factor out the greatest common factor. That's going to be our step to get this started. When we factor out 2x, we're just dividing it into all 3 of these terms. So 2x divides here, leaving 3x squared. Let me change the color though. 2x divides here, leaving a 5xy, so plus 5xy. 2 divides here, leaving 2x divides here, just leaving a negative 2y. So the x cancels out completely on this term here. And we have a familiar pattern, x squared, x, and no x's. X squared, x, and no x's. It's a little bit weird that we have a variable y in the mix. But you know what? That's not too hard to handle. So first step was to factor out the greatest common factor. The next step is factoring a little bit is not good enough if we still have a trinomial that factors. So next, factor this. We have to factor the trinomial itself. So the next step, we'll get 2x. Notice the 2x does have to come down. It's part of the total answer. So when you put these answers into the Newton homework, or maybe do them as a quiz, don't forget this part right here. It's a little easy to miss. Now, all we're doing is trying to factor the thing inside these parentheses. 3x squared could split up as a 3x times an x. That gets us started. A positive here, but a minus there tells us signs alternate. I'm not sure how they're going to alternate. I'll go with plus and minus. And if we're wrong, we'll just switch them up and make them go minus and plus. Finally, 2 is prime, so we don't have a lot of leverage with that as well. Maybe let's go 2 here. We need to bring in the variable y to get y back into the whole problem when we go to check our answer. And 1y here. So let's see how close we got. The check is on every single one of these. Multiply here to here. That's going to be xy. That's the inner product. Then the outer product is multiplying here to here. It's 3x times negative 2y, so that'd be negative 6xy. We didn't make it. We're going to 5xy, and xy minus 6xy is negative 5xy. Darn it. But if you're ever that close, this is all you have to do. Get out the eraser. It wasn't the 3x and the y, or the x and the 2y. It was just our signs. So let's just change up those signs, minus and plus, and see how it does now. Now this is negative xy. On the inner product, outer product is going to be positive 6xy. And positive 6xy minus xy is positive 5xy. We got the middle term, so that tells us the total answer is in fact this. So already our factoring techniques are kind of going together. We want to do the greatest common factor technique first, and then our trinomial factoring trial and error method next. Well, we did it, folks. That's our tour of factoring using the trial and error method. Any questions on getting through this one? Okay, there are more methods than trial and error out there. Sometimes I've seen people do interesting kind of like a diamond symbol with numbers in like different corners of almost looks like a baseball field, kind of a diamond. The other technique that the book discusses is using the AC method. So here's how this method will go. The AC method is really good whenever you have these kinds of problems. The leading coefficient is not a 1. However, when it comes to the AC method, it shouldn't be your one-stop shop, your go-to method for every single problem, because it turns out problems that look like these, where the leading coefficients are all essentially just a 1, These are really rapid problems with just basic trial and error. This one here, AC method, might have been not a bad idea. AC method might not have been too bad of an idea on this one either. And these are good problems as well for using the AC method. We should explain what we mean by AC in the very first place. What that's referring to is a trinomial has the form ax squared plus bx plus c, where a, b, c are real numbers. We assume that they're not zero, because if a was zero, then you just have two terms potentially, and it's not trinomial any longer. So it's the a here and the c here that's being referred to when we say the AC method of factoring. In this problem, the a would be 2, the c would be negative 20, and this is how the AC method gets started out. Take the 2 and the negative 20, and we multiply them together to get a negative 40. That's what AC is literally saying, take A times C. So multiply these. The AC method also works with the coefficient B. That's kind of confusing. It just doesn't strictly say it. So we take the B coefficient, which is negative 3, and we rewrite it like that. Now we have to solve two equations. The first equation is a multiplication equation. We want two numbers to multiply, result in negative 40. And the second equation, the one down below, involving the negative 3, let's convey that with the arrow as well. That one's going to be an addition equation. So we're really filling in the blanks. Whatever you put here, you put down below. Whatever you put here, you put down below as well. And even though it's not called the trial and error method, there is still trial and error. That's the downside about it. We need two numbers multiplying to negative 40, adding up to negative 3. Anyone happen to see what numbers they could be?
Is it 5 and 8?
Yeah, good call on that one. If you go say 5, 8 like this, we have to make one of them negative. And since we're trying to get the negative 3, let's go for this one negative. 5 plus a negative 8, yeah, it gives us the negative 3. So they multiply to negative 40, they add up to negative 3. That means it does the job. So this is step 1 of the so-called AC method. People like it because sometimes if you're solving two equations like this, it might give you more information and less trial and error in the problem. There's a little bit as you try to find which two numbers solve both of them at once. And here's the next step that we take. Take 2x squared minus 3x minus 20. And this negative 3, we just replace with those two numbers we just found. So this turns into 2x squared plus 5x minus 8x minus 20. So step 2 is to do this. It's actually a lot of steps. So that's the kind of downside about the AC method. We're doing quite a lot just to get to the factorization. But if the trial and error was hard in this problem, maybe we're actually saving time. Next step is just a review topic. Step 3, factor by grouping. It turns out those two equations that you see right up here, are like the magic equations that give you just the right numbers, that this is the one and only way it'll factor by grouping. That's kind of an amazing fact. Let's look into this. If this factors by grouping, we should have a greatest common factor here. And sure enough, yeah, x divides both. So GCF for greatest common factor is x. Likewise, now we want to be careful because we're going to factor out to the negative version of the greatest common factor due to that negative sign. But 4 divides here and it divides there. Looks like we can factor out a 4 on this one, negative 4 rather. Greatest common factor equals negative 4. So next step, actually make those factors happen, factoring out those greatest common factors. Factoring out x would leave us with a 2x here, plus 5 when we factor it from this term. Factoring out a negative 4 means put negative 4 in front. Divide negative 4 here, we get positive 2x. Divide negative 4 here, we'll get positive 5. That means 2x plus 5 has repeated. As per the last section, it means it also factors out. 2x plus 5 would go here. When it's divided out, you can put a little cancellation just to direct your eyes. All that's remaining is x minus 4. Then right at that step, we've got our right answer. If you attempted to FOIL this by trial and error, the 2x plus 5, x minus 4 is what would have done the job. Let's verify one core part. Here to here, that's the 5x. Here to here is minus 8x. And then 5x minus 8x, that is negative 3x. So that would be humongous numerical evidence we did it right. It's usually not as big of an emphasis on getting the 2x squared because we can just see 2x times x, yeah, that's 2x squared. Negative 20 is not as big of an emphasis as well because we can just eyeball that. 5 times negative 4 gives us the negative 20. The emphasis is always, how do we get the negative 3x? If we can land that, the whole problem is done. So it's a kind of a convoluted 3-step process, but it gives you just a little bit more of a hook to start the problem with less trial and error. And so that's where it can shine. Any questions at all, folks, on getting through this one? Okay, another thing I want to emphasize is when you go to do these problems on, say, a quiz or an exam, if you love the AC method, I'm never going to penalize you for when I think maybe you should have used the trial and error. And vice versa, I'm never going to penalize you if you use trial and error on this one, and I thought it was a good AC method type problem. In other words, if you give me the right factorization, that's what I'm really happy with. Use whichever method that seems the most obvious, the most natural, and you'll always be in great shape. So let's try this out once more. On 5x squared minus 12y squared. Let's copy the color coding. So here's how it starts. We take those two numbers and multiply. 5 times negative 12 is going to give us a negative 60. Then we take this number right here, the 17. We're going to have a multiplication equation and an addition equation. And let's see here. What jumps at me on this one is 60 is 4 times 15 would give me 60. I'm not going to hit a 17 that way. But also, let's see, why not 20 times 3? That'll give us a 60. We could go a negative 3 times positive 20. And negative 3 plus 20 is definitely a 17 on this one. So this one I think this one would have been trickier for me doing by scratch. It feels like there's more ways to go on this one. This one, I don't think this one was as too tough, but again, it just depends on the person doing the problem. Sometimes people are really good at factoring. Sometimes people have like a moment of inspiration. And now with those two numbers, here's the next thing we take. Those two numbers are just the one and only one way to break 17 up so that factoring by grouping works again. So we recopy the problem, 5x squared, but then we use these numbers down below, minus 3xy plus 20 xy minus 12 y squared. So really all I've done in this step is, well, we definitely made it look more complicated, but we broke up the 17 here. And that's just because from here to here, there's now a greatest common factor. Looks like all we can do is take out the factor x, so it's going to be a fast one. From here to here, a little bit more going on between 20 and 12. Looks like that one's going to be a 4 again. 4 goes in there 5 times, here 3 times. So it's going to be a greatest common factor of 4. I'm making it positive because the sign here is positive. But also there's a y and a y squared, so we can factor out a little bit more, a 4y. So on the very next step, factor out x from here, and this is what it would look like. X divides into 5x squared, leaving behind a 5x. Then minus. X divides here, but that's just a cancellation of x's now. It's just going to be a 3y. Then we go plus, because we're factoring out a positive 4y this time. 4 divided here leaves a 5. And y cancels off cleanly. It's just going to be a 5x. 4 divided into here is going to be a negative 3. Y divided into y squared just leaves us a y altogether. And that's what we were hoping to see, 5x minus 3y matching. Once we're there, factoring by grouping is over. Just go 5x minus 3y. We're factoring it out so it cancels. That same kind of visual pattern, just to help us grab the x plus 4y. At this stage, we've got it, folks. X plus 4y times 5x minus 3y. If you were to do this one by trial and error, those would be the numbers you would have gone for. It might have been a doable one trial and error, but I think the AC method actually was just maybe a little bit faster on this one, unless you saw right away what the combination is for trial and error to get to the right things immediately on the first try. But we did it, folks. That's our tour of looking into factoring trinomials. We'll factor a lot more in this chapter in our review section 6.4, later on when we're solving equations. And so this is really our just first look at it. We'll do more factoring topics in section 6.3 when we come back on Tuesday's class. But I think this is probably a good stopping point for us. Doesn't make sense to open a section with 2 minutes and some change. Well, any last questions at all then before we call it a night? Okay, well, it's been fun, folks. We'll continue on with the factoring topics next Tuesday, but have a great weekend. If you have any questions when you're working homework problems or otherwise, don't hesitate to email. I'll be happy to help out.